All right, I'm taking the roll now, so if you're on Zoom, please type something into the chat to let me know that you're here. And why is this not laptop? There we go. All right. So today we are going to be covering two topics, the first of which is total response of series and parallel RLC circuits. And then the second topic we're going to be getting into is how to solve general RLC circuits. So let's talk about total response first. That is not remotely how you spell parallel. All right. So you may recall from circuits 1 that the total response of a system, Y total, is given by the natural response of the system, Yn, plus the forced response of the system, Yf, where the forced response was really just what the circuit settled to at t is equal to infinity. Those same rules still apply. So let's say that we have the following circuit. Let's say that we have straight from textbook. So this is our circuit. And we can see that at t is equal to 0, our voltage source is getting switched into the circuit instead of being taken out. So what that means, so at t is equal to 0 minus, we can observe fairly easily that since there's no sources connected to the circuit, there shouldn't be any energy stored anywhere. But a long time after the switch has closed, when the circuit reaches DC steady state again, we should see that, let's see, there's going to be some energy stored in the inductor. Probably not any, well, definitely not any in the capacitor, because it'll look, the inductor will look like a short circuit with current flowing through it, which is why the inductor is storing energy. The capacitor is in parallel to that short circuit, which means the voltage drop over to 0, so the capacitor won't have any stored energy. But other than that distinction that now we have energy stored at t is equal to infinity, our analysis is pretty much the exact same as before. We just now look at the circuit at t is equal to infinity. So the first thing that we're going to need to do with any of these circuits is always to calculate alpha and omega naught. So the first question is then, is this a series RLC circuit or a parallel RLC circuit? So this is going to be a parallel RLC circuit, okay? So it may look like you have a 200 ohm resistor in series with a inductor and capacitor combination, but recall that the natural response is the source-free response. So during the transient condition with the voltage source turned off, meaning we replace it with a short circuit, that would put the resistor in parallel with the inductor in parallel with the capacitor. So this is a parallel RLC circuit. That's how the natural response will correspond with a parallel RLC circuit. So with that in mind, let me turn off this thing. Alpha is equal to 1 over twice RC. So that's 1 over 2 times 200 times 2.5 times 10 to the minus 6. Figure out what that's going to be. (1,000) nepers per second. Omega naught is 1 over the square root of LC. So that's 2.5 times 2.5 times 10 to the minus 6. That whole quantity to the negative 1/2 power. (400) radians per second. Since alpha is greater than omega naught, what type of circuit is this? Critically damped, overdamped, or underdamped? Overdamped, right? So before we get moving here, we should probably identify what our quantities of interest are. So I'm going to call this guy V of t. This is IL of t. This is IC of t. And so let's just solve for V of t for the sake of argument here. The easiest possible thing so that we can move along. So we're going to analyze the circuit at t is equal to 0 minus. So at t is equal to 0 minus, our voltage source isn't in, so it should be fairly straightforward that all of our quantities are 0. Do we need to actually do circuit analysis there, right? So if our voltage source is disconnected, there's no, and the circuit has been in such a state for a very long time so that we have DC steady state, then our inductor is replaced by a short circuit, so there's no voltage drop over it. Our capacitor is an open circuit, so there's no current flowing through the capacitor, so IC is 0, V is 0, and if there's no current flowing to the capacitor, no current can flow through the inductor as well because they're connected effectively in series. So we should have V at 0 minus is 0 volts, IL at 0 minus is 0 amps, and IC at 0 minus is equal to 0 amps just by inspection. No real circuit analysis required. Next, we'll analyze our circuit at t is equal to 0 plus. So now our switch is closed. So we have our voltage source is in play, which is 20. We have our resistor of 200 ohms. Here is where our inductor was. So our inductor current by definition has to be 0. So that's why it's going to look like an open circuit. So IL at 0 plus. Then our capacitor voltage was 0. So it's going to look like a short circuit. So here's V at 0 plus. Here's IC at 0 plus. So agree that this is what our circuit is going to look like at t is equal to 0 plus. So Again, because the voltage was found to be 0, that's why our capacitor voltage, or our capacitor looks like a short circuit. Because our inductor current was found to be 0 amps, it looks like an open circuit. That may seem counterintuitive, but that's the way it worked out for this particular problem. So V at 0 minus has to be the same as V at 0 plus, or excuse me, V at 0 plus has to be the same at V at 0 minus, because the capacitor voltage cannot change abruptly. And so this is 0 volts. IL at 0 plus has to be the same as IL at 0 minus. So if it was 0 amps, it continues to be 0 amps. IC at 0 plus is allowed to change. So what's it going to be? 20 over 200, so 0.1 amps, right? All righty. Lastly, we need to figure out what's going on at t is equal to infinity. So at t is equal to infinity, we are at DC steady state again, which means we're going to replace our capacitor with its DC representation, which is an open circuit, and we're going to replace our inductor with its DC equivalent, which is a short circuit. Here is IL at infinity, here is IC at infinity, here is V at infinity. This is 200 ohms. So V at infinity is what by inspection? Zero. This is a voltage drop over a short circuit. IL at infinity is what? 0.1 amps again, right? 20 over 200. And IC at infinity is 0 amps because it's the current flowing through an open circuit. So there's all of our circuit analysis taken care of. Now we can move along to our response equation. So this is really the only place anything changed other than the fact that we're having to do circuit analysis at t is equal to infinity. So our voltage, our capacitor voltage, V of t, because it's an overdamped circuit, will be of the form A1e to the S1t plus A2e to the S2t. That's the natural response. And then our forced response is plus VC, or plus V at infinity. Oh, let me, because that's not going to really change anything here, though. We'll see what happens. I mean, this is the correct equation for sure. A1 plus A2. Sorry. V at infinity. Right, and V at infinity has to be 0 volts. So let me just look through this thing real quick here. Yeah, okay. So I guess one thing that we should do real quick is calculate S1, which is negative alpha plus the square root of alpha squared minus omega naught squared. So that is negative 1,000 plus the square root of 1,000 squared minus 400 squared is negative 83.485. Sorry, not volts. Per second. S2 is negative alpha minus the square root of alpha squared minus omega naught squared. Negative 1,916.515 units of per second, because these represent the natural frequencies of the circuit, so they should have units of hertz or per second. All right, so V at t is equal to 0 plus looks like A1 plus A2 plus V at infinity. So this means that we're going to have, let's see, what was V at 0 plus? 0 volts is equal to A1 plus A2 plus 0 volts, gives us A1 plus A2 is equal to 0. I feel like I've made some dumb mistake here, but I don't see what it is, so we shall see. Because we're dealing with the capacitor voltage for equation 1, that means we need to deal with the capacitor current for equation 2. So IC of t is C dV by dt is C multiplied by S1 A1 e to the S1t plus S2 A2 e to the S2t, which reduces to C multiplied by S1 A1 plus S2 A2. Notice there is no plus IC at infinity term in the derivative relationship, right? Because when we take the derivative of this guy, this is a constant value, so that goes away. So you should not see a plus something at infinity term in your derivative-based relationship here. I want to be clear about that. All right, so IC at 0 was .1 amps. So we have 0.1 amps is equal to C, which is 2.5, is that millifarads or microfarads up here? Micro, thank you. Multiplied by S1, which we found to be negative 83.485. Per second times A1 negative 1916.515 per second times A2. This is our second equation, so we have a simple system that we can solve, which is going to give us a particular value for A1. All right, so system solver, 2x2 system, coefficients for first equation are 1 and 1 is equal to 0. On our second equation, we have 2.5 times 10 to the minus 6 times negative 83.485. And then we have 2.5 times 10 to the minus 6 times negative 1916.515. And this is equal to 0.1. Solve. We get 21.822 and negative 21.822 volts, which means V of t is negative 21.822 e to the minus 83.485 T, sorry, positive there, negative here, e to the minus 1916.515. Pardon? All right, second system solve. I can certainly do it that way. I use my calculator, and so I put the coefficient for A1 to be 2.5 times 10 to the negative 6. So 2.5 times 10 to the negative 6 times negative 83.485. And then 2.5 times 10 to the negative 6 times 1916.515. Oh, and that should be negative. Is equal to 0.1. Yeah, still getting 21.822 and a negative 21.822. Anybody else getting different things? We got. And volts. So I guess this was a poor example problem, or at least choosing the capacitor voltage as the thing that we find, I guess was a poor example here because there is no DC offset. Okay, so let's find, for the sake of argument, the inductor current, because that one is going to have an associated DC offset that goes with it, right? Because it settles to some value that is non-zero at t is equal to infinity. So IL at of time is going to be A1 e to the S1t plus A2 e to the S2t plus IL at infinity. So IL of 0 plus is going to look like A1 plus A2 plus IL at infinity, which was 0.1 amps. IL, or sorry, which means we have IL at 0 plus was 0, right? 0 amps is equal to A1 plus A2 plus 0.1 amps, which gives us A1 plus A2 is equal to negative 0.1 amps. VL, or V of t, sorry, is given by L DIL by dt, which is going to be L S1 A1 e to the S1t plus S2 A2 e to the S2t. And the S1 and S1 and S2 are the same for everything in the circuit, so we don't need to recalculate those guys. So from this, V at 0 plus gives us L times S1 A1 plus S2 A2. V at 0 plus was 0 volts, so we have 0 volts is equal to L, which doesn't matter because we can divide both sides by L to get rid of it. So S1 was negative 83.485. Sorry. Per second. A1 plus negative 1916.515 per second. A2. So here's our first equation. Here's our second equation. solving these guys, we'll find A1 and A2. So I have 1, 1, negative 0.1, negative 83.485, negative 1916.515, 0. So I get A1 to be negative 104.554 milliamps. A2 is positive 4.554 milliamps. From this, IL of T is negative 104.554 e to the minus 83.485 T plus 4.554 e to the minus 1916.515 T plus 0.1 or plus 100 milliamps would be a better way to put it. So there is a DC offset. That's the most common mistake that I see made, is that you calculate A1 and A2 and forget to put in the quantity at T is equal to infinity. Yes, sir.
Third line from the bottom. Aren't you supposed to be multiplying that by L?
So the reason why I didn't bother multiplying by L is if I divide both sides by L, 0 over L just gets rid of that common factor. Yeah, so that was just me being able to punch it into my calculator quicker by recognizing that. So if that were a non-zero value, I would absolutely need to remember to multiply through by L. Yeah, so. All right, so this is really the total response of series and parallel RLC circuits, in a nutshell. Really, the only different things that we have done here are we analyze the circuit at T is equal to infinity, and then we added that information into our representative equation, and that's already put in your tables. So it's the exact same thing that we did before, except that y at infinity isn't by definition 0. So you guys ready to move on to, I guess, a more difficult but more comprehensive way to look at these things, right? Because series RLC circuits are pretty easy. Parallel RLC circuits are also pretty easy, but unfortunately, the overwhelming majority of circuits aren't going to be simply series or simply parallel, so we need to look at how we might approach those guys. So we're going to revisit a couple of things here just real quick because I want to show you guys something. So let's say that we had, let's revisit, in effect, the parallel RLC circuit, okay? R L and C. Where this is IR, this guy is IL, this guy is IC, and this is our common voltage. So just so I don't make a mistake here that I'll have to figure out later, I'll go through and actually derive this again. So we know that IR plus IL plus IC is equal to 0 by applying Kirchhoff's current law at our topmost node. And this is actually, you've already taken notes on this when we were setting this up, so you can actually just kind of pay attention for a minute because all of this is here, or all of this has already been covered. So this gives, let's see, I is V over R. So we have 1 over R times V. Let's see, the current through an inductor in terms of the voltage is, or sorry, the voltage drop over an inductor is going to be L. No, that's not right. And then we have C dV by dt is equal to 0. Integrate differential equation, take the derivative of both sides, and we're going to divide everything by C as well, which leaves us with the second derivative. Sorry, that's a T. All right. And we know that for a parallel RLC circuit, alpha is 1 over twice RC, and omega naught is equal to the square root of 1 over LC. Right? We've shown that. That's how we've actually defined them for the parallel RLC circuit. So if we look at this coefficient right here of our differential equation, which is the coefficients of our characteristic equation, right? When we make in our substitution of V of t is equal to A e to the st, we have A times s squared plus 1 over RCS plus 1 over LC multiplied by e to the st. That's how we got all this thing here. So if we call this coefficient B and this coefficient C, we can see pretty easily that alpha is simply B over 2, and omega naught is simply the square root of C. For a series RLC circuit, L and C, where here's our common current I, here's our voltage drop VC, our voltage drop VR, and our voltage drop VL. Doing KVL around the loop during the transient condition gives us VR plus VL plus VC is equal to 0, which is R times I of t plus L times DI by dt plus 1 over C integral from T naught to T I of x dx plus VC at T naught, sorry, is equal to 0. Integrate differential equation. Again, we take the derivative with respect to time on both sides, and we're going to divide both sides by the coefficient of our first derivative term. So we're dividing both sides by L. So this gives us the second derivative of I with respect to time plus R over L times the first derivative of I with respect to time plus 1 over C times the current is equal to 0. And again, we know that alpha is R divided by twice L, omega naught is equal to the square root of 1 over LC. Sorry, this should be LC here. And so if this is my coefficient B and this is my coefficient C, we again see that alpha is simply B over 2 and omega naught is the square root of C. So it doesn't matter whether or not it's a series or a parallel RLC circuit. We can determine alpha and omega simply by the coefficients of our second order differential equation, which means if we can come up with a second order differential equation for either the voltage drop over a capacitor or the current flowing through an inductor, we can generalize this result to any RLC circuit, regardless of whether or not it is a series RLC circuit, a parallel RLC circuit, or other. So that is all what solving general RLC circuits is forcing your way through the math to figure out what that differential equation is going to be. So let's take a look. We'll probably have time to do literally one example because these can get a bit tedious. Okay, so let's say that I have the following circuit. I have some source voltage Vs. I have some resistor Rs. Here's my switch. I'm not quite sure if I'm going to open it or close it yet, so we'll circle back around to that guy momentarily. Let's call this guy R1. Here's an inductor L. Here's a resistor R2. Here is a capacitor C. All right, so we need our switch to be going down here at t is equal to 0. The reason why I say that is if we were analyzing this circuit with the switch opening, then during the transient condition, this would be a series RLC circuit because R1 would just be in series with R2. That would be easy to solve. But with the switch closing, during the transient condition, with our voltage source turned off, we have this resistor Rs in parallel with the series combination of R1 and L1 in parallel with the series combination of R2 and C, which is not a parallel RLC circuit because they got 2 extra resistors, and it's certainly not a series RLC circuit either. So this is one where the only way to solve this is using the general method by figuring out what the differential equation is and then determining the coefficients of the differential equation and using that to calculate alpha and omega naught. That's going to drive me insane. So let's talk about how we might go through that. So we're going to define a couple of important quantities here, okay? Here is our voltage drop over our inductor, VL of T. Here is the current flowing through our inductor, IL of T. Here's the voltage drop over our capacitor, VC of T. Here's the current flowing through our capacitor, IC of t, and we need to keep in mind that VL of t can be expressed as L di by dt, and similarly, IC of t can be expressed as C dVc by dt. Okay. So unfortunately, there's not really a simple formulaic way to approach this type of problem. Okay. So we really kind of have to throw the kitchen sink at it. And so let's think about some different equations that we could generate. We're probably going to need a couple, at least 2 or 3, and we're going to have to bother doing some substitution. So one thing that I could say is that during the transient condition, these 2 branches are in parallel, right? So I could say that R1 times IL of t plus VL of t is equal to R2 times IC of t plus VC of t, right? I know that has to be true. Now, if I make my substitutions in here, so this is going to give me R1 IL of t plus L DIL by dt is equal to R2 R2C dVc by dt plus VC of t. Okay. So I've got everything on the left-hand side expressed in terms of IL of t, and everything on the right-hand side expressed in terms of VC of t. So now I have to figure out some relationship that I can get to that will allow me to relate those 2 quantities directly. So I need to relate either IL to VC or dVc by dt, or vice versa. I need to relate VC to IL or VC to the derivative of IL. Oh, that's the guy in chat saying that he's here, I think. Yep. All right, so how might we go about doing this? Where can we develop another equation? So this is, we're going to be doing all of this analysis and all this kind of stuff. We're trying to figure out what's going on during the transient condition. During the transient condition, that switch is closed, right? So we could say, we could call this current for now IR. Okay. And by applying Kirchhoff's current law, we know that IR of t is equal to IL of t plus IC of t, and I'm going to go, we'll leave it there for now, okay? So that is a direct relationship between IL of t and IC of t, where IC of t could be expressed in terms of the derivative of the capacitor voltage. Now we need to figure out, we've introduced a new variable here, IR. So we need to figure out how to put that in terms of something useful, right? So IR is going to be simply 1 over RS multiplied by VS, the voltage on the positive polarity or the left-hand leg of the resistor, minus either the voltage drop of this left-hand, the total voltage drop over the left-hand branch, or the total voltage drop over the right-hand branch. They represent the exact same quantity, right? So this is just nothing but good old Ohm's law. So here is really where we're going to decide if we're going to get our differential equation in terms of our inductor current or our capacitor voltage. So pick one. Inductor. All right. So minus R1 IL of t plus VL of t, which is L di by dt. So that is our resistor current is equal to IL of t plus C dV by dt. We okay with the math here? This is where bookkeeping is going to get real wonky real soon. So what I'm about to do, first and foremost, is I'm going to subtract an IL of t from both sides. Okay. So let's be explicit here so I don't make a mistake. We're going to have VS over RS minus R1 over RS IL of t plus L over RS DIL of t by dt minus IL of t is equal to C dVc by dt. Rearrange this just a smidge as VS over RS minus 1 plus R1 over RS times IL of t. Hold on a second here. This should be a minus sign because it's minus positive, so that should be a minus sign there. So the bookkeeping is where things get real difficult here. All right. Minus L divided by RS times DIL by dt is equal to C times dVc by dt. We all in accord here. The last thing that I'm going to do is then divide both sides by C. So this is going to give me, I'm going to rearrange this slightly. Negative L over RS times C times the derivative of IL with respect to time minus 1 over C times 1 plus R1 over RS IL of t plus VS divided by RS times C is equal to dVc by dt. We okay with that algebra? All right. Now I'm going to look back through here to see what I can do. So I have the derivative of my capacitor voltage in terms of the derivative of IL and IL itself and a constant term. So my thought here is substituting in what I have for dVc by dt right here. Because what's that is going to give me is then Vc with everything over here in terms of IL, either IL and its derivative. And then what I could do is take the derivative of that relationship. So I would have the second derivative of Vc in terms of everything expressed in terms of IL is equal to another representation of the second Vc where everything is in terms of IL as well. I'm trying to think if there's a less punishing way to do this. So give me a second to think if I can come up with another relationship here. So we've done KCL. It's the fact that there are two resistors in here that are, if R1 or R2 weren't in here, this would be much easier. Let's see. Because I don't have any equations with the second derivative, so I can't just do that. So this big block right here is me just manipulating the same equation. So making any substitution into there isn't going to help me do anything. I'm just trying to kind of organize my thoughts here real quick. All right, I guess this problem we're just meant to suffer. All right, so I'm going to call this guy down here equation 2. And I am going to attempt to substitute equation 2 into this guy right here, which is equation 1. So I'm going to have R1 times IL of t plus L DIL by dt minus R2 times C of dVc by dt. where dVc by dt is this big ugly fella, negative L over RSC DIL by dt minus 1 over C 1 plus R1 over RS IL plus VS over RSC is equal to VC of T. So let's combine some like terms and all that jazz. First, there's a common factor of C and all this. So this C cancels out this guy, and this guy. So that at least makes it a little bit easier. So I'm going to have R1 IL of T plus L DIL minus plus, let's see, so negative R2 times negative L over RS gives me R2L over RS positive DIL by dt. Negative R2 times negative gives me positive R2, 1 plus R1 over RS times IL. And then I'm going to have negative R2 VS over RS is equal to VC of T. I can group like terms. And so let's see. That's going to give me R1 plus R2 multiplied by 1 plus R1 over RS times IL of T plus L times 1 plus R2 over RS DIL by dt minus R2 VS over RS equal to VC of T. All right. So let's double check my algebra here. Anybody see anything horrifyingly wrong? All right. What I'm going to do now is I'm going to take the derivative of this guy with respect to time. I know, but it's actually a lot easier than you think, right? Because all this ugly stuff right here is just a constant, and this is just a constant. So when I take the derivative of this guy, what I'm going to get is R1 plus R2 times 1 plus 1 over Rs times the derivative of IL of t with respect to time plus L times 1 plus R2 over Rs multiplied by the second derivative of IL with respect to time is equal to the derivative of VC with respect to time. So let's call this guy equation 3. All right. Now, what's interesting is that equation 2 and equation 3 are big chains of things expressed in terms of IL that equal to this derivative of the voltage with respect to time. So I can set these two guys equal to each other, and I will have a really ugly equation that has no capacitor voltage anywhere in it, right? So if I set, good Lord, I'm running out of room here. Equations 3 equal that is going to give me R1 plus R times 1 plus R1 over Rs DIL by dt plus L 1 plus R2 over Rs times the second derivative is equal to negative L over RSC DIL by dt plus 1 plus R1 over Rs IL plus, sorry, that should be a minus sign. Vs over RSC. Now, in a group like terms again. So let's start with our second derivative term. So a second derivative term, we have L multiplied by 1 plus R2 over Rs our first derivative term, we are going to have L over RSC plus R1 plus R2 times 1 plus R1 over Rs times the derivative with respect to time. All right, so just to be clear here, I've taken care of this guy, I've taken care of this guy and this guy, plus 1 over C, 1 plus R1 over Rs, IL is equal to Vs over RSC. So that means that alpha is going to be L over RSC plus R1 plus R2, 1 plus R1 over Rs divided by twice L1 plus R2 over RS. So I just took this coefficient and then divided it by twice this one. So that's going to give us alpha. And then omega naught is the square root of 1 over C times 1 plus R1 over RS divided by L 1 plus R2 over RS. To the 1/2 power. Which just for the sake of argument, I'm going to show you guys something. We're going to have omega naught equal to 1 over the square root of LC. It's just multiplied by a scaling factor. If I did my math right. So RS, plus, R1 plus RS, and then R2 plus RS. Yep. So at this point, we could plug in numbers and then approach the problem like we would do any other problem. So as you can see, it can get extraordinarily tedious. Okay. This one was a little harder than I thought it was going to be, or at least a little bit more time consuming. So what we'll do on today's Wednesday, right? So what we'll do on Friday is we'll look at a problem that has 2 capacitors in it that are that can't be combined, because that's also an example of a second order circuit, or we could have one that has 2 inductors where they're uncombinable. So yeah, so this is your life, because you chose to be an electrical engineer. It's just doing terrifying amounts of differential equations. Technically, we could keep on doing this for 3rd, 4th, and 5th order and all that kind of stuff, but there becomes a point where this is much, much easier to do using Laplace transforms. So this is as hard as it's ever going to get without using tools to make things significantly more simple. Any questions other than, good God, why? Pardon? Yeah, probably so. Like I said, this problem was made significantly more complicated by the fact that there were 2 resistors. And so what I mean by that is if resistor R2 didn't exist, then we could have said R1 times IL plus L di by dt was equal to VC, and then taken the derivative of that and then did KVL around this loop, and we would have been done. But that's the extra resistor in there is what made this guy wildly more difficult. So I'm trying to think now off the top of my head. If we could have used Thevenin's theorem to simplify things at all, because if we can make this look like a 2-terminal network by disconnecting something and doing simplification, that might have been something there, but I don't know how we could get the resistor and, or excuse me, the inductor and the capacitor out and still leave this as a 2-terminal network. I think that would make it a 3 for this particular configuration. Anyway, yeah, this is problems won't be as horrifying as this. They'll be annoying because there's no way they're not going to be, but they won't be as bad as this guy. Yes. So here's why I didn't use real numbers. It was hard enough doing the algebra symbolically here. If I had thrown real numbers in, this would have been an absolute nightmare. My personal preference is to work everything symbolically and then put in real numbers. And you have to put in real numbers here because once we calculate alpha and omega naught, that's what tells us the numerical values of alpha and omega naught tell us whether the system is critically damped, overdamped, underdamped, and how to proceed. This is all the setup to be able to do part one or part A of calculate alpha, calculate omega naught, blah, 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 for this particular circuit. All right, I've punished you enough for no good reason. So I'll see you guys on Friday.